Hi, Zubin.
Hi.
You'll go first, huh?
Yeah, okay. I'll just finish up the demo.
Yeah. That yes, the mutex example, for a simple instrument or anything else that you want to add. I mean, I had this one question. Okay, and I think USMV, does it support both CTL and LTL?
Yeah, it does support both.
Yeah, but I guess it does not do CTL star.
I'm not sure about that. Yeah.
Okay, they can try it because the way I have done is, I mean, in previous things, I usually do bottom up and I start with either introducing LTL first, CTL, and then go to CTL star. I never, or sometimes I never do. But this time I'm trying differently because that's how it's in the book. But I started with CTL star. And
Yeah.
then today I introduced CTL and LTL as specialization, sublogics of CTL star. So they can try it on their own. I doubt if CTL star is supported.
Yeah, I don't think it is. Doesn't seem so.
We'll wait for a few more minutes, huh?
Okay.
Still a couple of people. So there are 1, 2, 3, 4. 2, 3, 4. I'll make you a host.
My screen should be visible now.
Yeah, it is. You should start at 3:35. That's reasonable, no?
Yeah.
Yeah, go ahead. Zubin?
Yeah.
Uh,
So I'll start.
Go ahead. Usually Diganta joins, but today he's not there.
Okay, so we'll be looking at an example of mutual exclusion, how we can model it in new assembly. So mutual exclusion is when you have multiple processes trying to access a shared resource, and you don't want more than one process to access it at the same time. So you might say have a file, and you don't want more than one process is writing to the file at the same time, because then the file will end up coupled with interleaved output or a network socket or any kind of resource where you only want one person accessing it at a given time. So all the processes need to coordinate with each other to decide who gets to access it, and make sure that both of them don't access the resource at the same time. So in USMV we can model it in this way. So uh, first we have so we're going to use a semaphore for uh, communication. So a semaphore is basically is a boolean variable that allows us to communicate whether a process is accessing the critical section or not. So the critical section is the section where the process is accessing the resource. So if you look at all the possible states of a process, it can be idle, where it's doing something not related to the mutex. It can be trying to enter the critical section. It can be inside the critical section, or it can be out of the. It can have left the critical section. So, uh, so the way we model asynchronous processes in new SMV is we use this uh, process keyword. So both of these processes, proc1 and proc2, will be running asynchronously. So proc1 might take a step and proc2 might remain in the same state, or proc2 might take a step and proc1 might remain in the same state, or both of them might simultaneously take a step. So that is what asynchronicity means.
No, no,
Uh,
no, no. Asynchronous cannot. Two cannot take
yeah,
simultaneous.
yeah, don't take simultaneous steps. So each process takes a step.
Yeah.
At most, yeah. So one of these
At
processes
most
will
one
take a
of them.
step at each point. Yeah, or both of them might not take a step also. So
No, that I don't know.
there might be. I mean,
I
it's not
don't think it does. Okay, so
live,
the
right?
way I have formally defined is not at most one, exactly one. Okay.
Okay,
Yeah. So
but
I think the
uh,
condition that both of them keep idling is usually not the way asynchronous interleave semantics is defined. Okay. So yeah.
yeah. Okay, so we see that both processes first they have access to a shared variable, which they will use to coordinate, and
In the example
the
we
any
saw in the class, turn, I mean, semaphore was
yeah,
turn. Yeah.
yeah. So for two processes, you do need a boolean variable. So it can be a turn, it can be a boolean. So, but it has two possible values. So this example is slightly different, but
Okay.
yeah. So we start at an idle state, and uh, the next state, if our current state is idle, we can either remain in the current state or we can try to enter the critical section. So when we are entering the critical section and the semaphore is false, which means the critical section is not occupied by any other process, then we can actually go ahead and enter a critical section. Uh, and if we are in our critical section, we may continue in our critical section or we may finally exit. And uh, once we exit, we are back in the idle state. Uh, the next condition for the semaphore is that um, if
What does
a
the true
process
at
is
the end mean?
So this is just a catch-all case. It isn't really necessary, but new SMV gives some warnings because uh, oh, so true. It's not a catch-all case in this case because uh, if none of these cases happen, then it'll just proceed in its current state. So the state is the same as the current. So the next state will be the same as the current state. So this case will only be reached if entering is state is entering and semaphore is true. So that means that some other process is already in the state.
Yeah, it's like the else case.
Yeah, it's
If
like
an
the other,
else
yeah, the
branch,
catch-all, the fall, yeah,
yeah.
the case that will be executed if none of these previous cases are true. So, and for the semaphore, so we also have to make sure that the semaphore is updated. So the semaphore is initially set in main as false to indicate that uh, no process is trying to enter the critical state. But the way the semaphore state advances is if the state of the process is entering, then it's set to true, and if it's exiting, then it's set to false. In any other case, it's remains in its current value. So this is an example of one way you might implement mutual exclusion for two processes. So we can uh, verify some properties about mutual exclusion. So let's just see first. If I comment out this line, I'll explain what the fairness line does in a bit. But if I comment this out right now, and then I try to uh, verify this, sorry,
Yeah. In case you're wondering what LTL is, you will see later in the class that LTL is a sublogic of CTL star, which permits only path formulas. Okay? So we will introduce
so
that formally today, later in the
yeah,
class, but yeah.
yeah. So the first condition is says that uh, always this G, like I mentioned last time, also G means always some condition is true. So no matter what, in every state, this condition must hold. So the first condition says that it is not so that process one is also in the critical state and process two is also in the critical state. So this is the mutual exclusion property that both processes can't be in a critical state at the same time. We can write another uh, specification that says uh, that ensure that if a process tries to enter the critical state, it will eventually succeed in doing so. So we can encode it like this. So we say that always, whenever process one is in the entering state, eventually it will get into a critical state. So F means eventually. So it will eventually succeed in entering the critical state. So this is a starvation freedom property. This is what it's called. So that no process is starved for work indefinitely. Eventually, it must proceed into the critical section if it tries to do so. So crucially, this is not that it doesn't say that uh, this property would say that it enters the critical section in its next state, which can't be true because the critical section might be the semaphore might be true and the other process might be in the critical section itself. So we use the eventually property to state that this must happen at some point in the future, maybe if not now, then later. So if we try to verify the second property, new SMV could verify that the first property was true. But if we try to verify the second property, uh, it gives us a counter example. Uh, and the counter example, it generates some states. Both processes are in the idle state. Uh, then process 1 goes into the entering state, and uh, after that, uh, yeah, process uh, process 1 goes into the entering state, and then nothing happens. So process 1 uh, doesn't run anymore. So if you notice in this output over here, so this counterexample is that if process 1 uh, goes into the entering state, but after this it doesn't take any further transitions. It doesn't uh, try to get into the critical section at all, because it never runs after this. So in that case, this property is clearly violated. So uh, over here, if we see in the output, we see the special variable running, which is not anywhere. We didn't define this variable anywhere over here. So the running variable is a special variable that's implicitly associated with the asynchronous processes. So asynchronous modules that is true when the process is taking a step, and is false when the process is idle. Not idle in the sense of the state idle, but idle as in it's not uh, making any taking its next transition. So we can so we would so this property is clearly not true, but it is true if we assume a fairness condition. So fairness condition is a condition that must be true at every step of the transition. So the fairness condition ensures that uh, the process runs. So we can add a fairness condition
No,
here
no, no.
also.
Okay. So here's a correction. Okay, in general, what you just now said is too strong a fairness. Fairness in the general case, what it says is that whatever that you specify there, okay, this running just means, yeah, that condition, that event
Yeah,
should happen
infinitely often.
infinitely often. It
Yeah,
doesn't mean that it has to happen every time, okay? So it has to
yeah,
happen infinitely often. So in this
yeah. Sorry.
case, the running is the kind of the event that is associated with that a particular process is selected, okay, to make the transition. So what you're saying here by saying fairness running means that each process should be selected to make its transition infinitely often. So what is specified in fairness is some kind of an event, okay, you could say. We will talk more about that.
You can write any kind of condition here, but
In
you know,
general, you could
so
think is a state, okay? It's a
it
condition.
takes that as an assumption when it's checking these LTL
Yeah.
properties.
Yeah, and that condition should happen infinitely often, and it selects those paths on which that condition that is stated as part of fairness happen infinitely often, and it checks only for those fair paths.
Yeah. Okay. So now let's see. So we've added the fairness condition. Let's see if our starvation freedom property, this one, is true. So it does come up with a counterexample. Yeah. Uh, let's see. Uh,
We'll say correct, checked, or did it?
no, it gave a counterexample. Let's see.
Yeah, the way you coded this one is not exactly the way I've coded in the class, so it is not clear what went wrong.
Mm. Process 2 is entering, then process 2 enters the critical state. Process 1 starts running. Uh,
No, you will have to say that both process, no? So there's a running 1 and running 2. Each process has running 1 and running 2.
yeah, so it's over here, right? So it's for the module. So the fairness condition holds.
I'm not sure. I think there is each process is associated with a running, okay?
Yeah.
And I thought that you'll have to say running 1 and running 2. In,
You can do that, but
no. Yeah, but
over here,
huh?
this is per module. So this fairness condition is
Right.
associated with this module, and it's instantiated twice, right? So the fairness condition will also be instantiated twice implicitly. Let's see. So it says that proc1 dot state equals entering, but proc1 dot state never. Okay, proc1 dot state equals entering. Here,
So it is
it's much.
switching between proc1 and proc2.
Yeah.
That it is doing.
So proc1 is entering. Proc1, proc10. Eventually, proc2 starts entering. Semaphore is true. So proc2 enters the critical state. Then proc1 starts running. Um, proc1 stops running. Proc2 starts running. Proc2 is out of the critical state.
See, okay, what is the, no. See, see, if you use a semaphore, the other one should be the inverse of this. I mean, have you created identical modules?
Yeah.
No, then it won't work.
No, it should, I think,
No,
because
no, no,
look,
no.
we have
If one
mutual
is
exclusion,
trying to
but
enter on sem, oh, but that should by.
we have mutual exclusion. We don't have starvation freedom. I did test this earlier and it seemed to work.
Why don't you just say, so you've done some modification here where you go from exiting to idle and then from critical to exiting and then you go to idle. Yeah. I don't know what you mean by state idle means you could be either in idle or entering. See, but you can, well, I mean, you have, oh, I don't know why you may have made this kind of a thing. So you can idle for however long that you want.
Yeah.
I mean, the way you've defined it is when you're an idle, you can keep on idling.
Yeah.
So, so if the other process continues to idle, oh, you made some changes here. So it's difficult to analyze this. I mean, obviously this is wrong, okay? So because you allow each process to kind of never come to entering.
No, but process one is entering. So in the counter example, we have process one entering. Then process one doesn't make any progress, but process two enters and exits the critical state. So process two enters into critical and then it exits.
Uh, then?
And then semaphore is set to false, which is fine. And
So process two is an idle.
process
Go.
two is an idle, and
Does
that's
it
the
ever
end
go
of
to
the.
anything?
No, there's nothing after this. So that's the end of the counter example. Oh, so I think this is doing bounded model checking. So no, it always generates the same. I think. Okay, so I'll debug this later and get back to you at the end of the class. But if we remove this property, we can see that so mutual exclusion holds. But suppose we remove this check for the semaphore over here, so it enters into the critical section always. We can see that mutual exclusion is also violated if we remove the check. So this is how you can use new SMB to model processes. So any questions so far?
Yeah, let's why don't you correct that, okay, and see
Yeah.
what's going wrong. Either it is not doing, why is it stopping there? That's an interesting thing. Or the fairness condition is not exactly correctly specified. Okay, my memory is a bit rusty as to how you do it. I thought you couldn't do it like this. I thought you have to do it globally by saying. Somadev Mall has something, question. Why don't you ask openly to the class, Somadev? Should we have the second constraint for process two? That's what I was thinking,
You
okay?
can have that, but
That is what I was thinking. No, I think, I mean,
you
Zubin
can do this also, but
assuming that if you, no.
you can have this constraint also, but
No, but that is not a constraint. That's two separate properties,
yeah,
okay?
that's two separate properties, but you
Yeah,
have
but what
such a property for each process,
you
right?
are
And it
saying
should work, right?
running will ensure that just by processing running, it will ensure. The way I would have done it is to have running one and running two, okay, for each process. And then say the fairness condition is running one and running two, okay, so that each of them will be, will ensure. So that's the way
So
that I've done.
no,
Now, I don't know about
so we can do that also. We can do
whether it makes a difference or not, yeah.
proc one dot running.
It's a comma, I think, so that you can specify, is it or? Okay.
XOR, right? Or we can do
Why
exclusive.
exclusive or? The way, at least conceptually, is you specify, give a bunch of events. It's a set of events, okay?
This is not a correct fairness property because it can just be proc one running and proc two never runs.
We need to look at this, how exactly fairness is specified. So rather than floundering around, okay?
But I think the fairness property is fine.
Oh, you think your transition system is...
So I have a question regarding the syntax.
Okay.
So how would we like what is the end of the module section, like how would we specifying that the fairness condition is part of the module semaphore? I mean the user module.
So I think it just one module to the others. So where like this is where one module begins and it ends where another module begins.
I see. Okay.
What was the question? So how do you specify?
Different modules, like where does one module start and another one begin? So module main
I think
starts over
fairness
here
must
and
be the part of main module,
no, it's
not like it.
no, it has to be part of this module. So yeah. Okay, so any other questions?
Okay. Yeah, so there is some work to do here. Okay, we need to get this debugged. Okay,
Yeah.
either your thing is wrong, you have to debug, or the way that you're specifying fairness is not exactly correct. Okay.
So we can specify multiple fairness conditions in
Yeah,
separate lines, right?
that's the way that I would have done. Okay, conceptually, I would have running one and running two. And then I will say that running one, it should not be ignored, okay? Which is not exactly that way.
No, that doesn't help. If you can specify it like this also, but it's easier if you specify it once for the whole module.
I see. Then why do you think it's not working?
It gives the same failure condition. So
Okay, so rather than, why don't you debug, okay?
okay, yeah,
And what you should also do is exactly recreate the example that I used in class, okay?
yeah,
You've done some change here, which needs to be debugged, okay? You can do both. But I hope you got the idea, okay? So we will debug this, okay? So Zubin will debug this and then clarify. So shall we move on? Okay, Zubin?
yeah. Okay, I'll stop.
So do you see my screen?
Yeah,
Yeah, I'm a bit rusty about the exact the syntax and the how you do it in USMV. So I can't help you there. So when you debug it and come back. Yeah.
yeah. Okay,
Okay. Thank you. Yes. So in the last class, we saw syntax of CTL star. We saw the distinction between state formulas and path formulas. Okay, and CTL star was constructed as a state formula which had embedded path formulas. Okay, and we saw defined the formal semantics of CTL star. And we saw some example formulas in CTL of state formulas, path formulas, and formulas in CTL star. So CTL star is a state formula, okay, eventually at the top level. So just to summarize, the main components of the formal semantics is defined in terms of as a satisfaction relation given for path formulas, given a model, a crypt key structure, and a path to define when a path formula is satisfied by that path in the crypt key structure. And a state formula, you need to give it a state, is relative to a state in that model. Satisfaction is defined with respect to that. So model checking in any temporal logic is defined as, this is written this way, and what it means is that for every initial state of the model, MS, psi should hold for every initial state in the model. Because of the way that this thing is defined, that it has to be hold for every initial state, it is quite possible that you can have this condition, okay, that for some formulas, both psi and not psi may not hold. Okay, because it may, for some initial state, it may hold, and for some initial state, it may not hold. Okay, so that is kind of one observation that I wanted to make, because in classical logic, when you have propositional logic or things, this usually the negation one of them will the negation is defined in such a way that one of them will hold. But here, because the satisfaction, satisfaction with respect to a model is defined, that it should hold good for all initial states, that it is, this condition is a consequence of that. Okay, so that's all. Okay, so that you should be aware of. Okay, and that's the observation here. Another thing that I forgot to mention last time is we can define equivalence between formulas using this satisfaction, model checking satisfaction relation. So when we say that two formulas in a logic are equivalent, what it means is that for all models, of course, with the same labels, set of labels, label set, that when one formula is satisfied, if and only if the other formula is satisfied. So this is classical notion of equivalence, even in classical logic. Okay, so that's how when you say that two formulas are equivalent, this is what we formally mean. So what I want to do today is to, this is the outline. I'm not exactly in this order. I think I will first introduce CTL and LTL as sublogic of CTL star. I'll quickly define that. And then spend some time looking at some toyish examples and some more, more complicated examples to warm you up. And then talk more about some normal forms for formulas in CTL star, and I'll also compare CTL versus LTL. And later on, we will see a classification of properties into safety and liveness, which Zubin mentioned on the way. But this is a formal classification of properties based on the kind of counterexamples that they have. And then we'll be revisiting fairness when some of the the issue that we faced. Hopefully by then we would have solved the mystery of how exactly fairness needs to be specified and why that example was not running on a new SMB.
I figured out the problem. So.
Okay. Do you want to take over?
No, the problem is pretty simple. It's that the property actually is not true for our.
Well, that's why. I mean, so your transition.
So because the loop is
worth explaining so that we will not be on tenterhooks. Okay, since I'm not kind of got into it, I will stop sharing. Okay.
Okay.
And why don't you clear that so that we'll be. Go ahead and share. What was wrong?
Okay, can you see my screen?
Yeah.
Okay, so this property says that if proc1 tries to enter the critical section, eventually it will do so. Mm-hmm. So new SMV was giving us a counterexample. So it has some states, and over here it says loop starts here. So the loop it says is that first proc1 is tries to enter the critical section. Then there's a loop. So the loop is that proc2 enters the critical section, then proc2 does enter the critical section, and then it exits, and then it keeps looping. So proc2 keeps entering and leaving the critical section, but proc1 never actually has the chance to enter the critical section because.
Why so? Because the way that my example I had set turn 1 to be 1, then it would set turn to be 0. Okay.
Okay. Yeah.
Always give the other a chance. Okay.
Yeah.
Which you probably are not doing. Huh?
Yeah. So this example does not actually ensure starvation freedom. So another.
So you need what is
another
called
different
So
algorithm.
even if you assume that every process is given the same, given a chance, this is not okay. The thing can ignore because you have created. Why?
So the
Because
algorithm does not
the algorithm
this.
itself is not the thing. So because you have created an ideal in semaphore, I mean you could. Both processes are entering the critical section under the same condition, okay, correct?
Yeah.
Of the semaphore. And therefore, okay. Did people get it? See, there was one crucial difference between this, and I kind of asked Zubin about that. In the example that you showed that I showed in class, I used a variable called turn, okay? And the turn was in the critical section before it exited, each process was setting it. One process was setting it to 1, the other process was setting it to 0, okay? So that's why, as long as you took care to see that each process was given a chance, it would satisfy the starvation freedom. Whereas here, one process can be continuously be
Occupying the critical section.
yeah.
So I think the other sorry.
Yes. Sorry. So is this what's happening, that the other process is only being scheduled when the first process is in the critical section, and at that point
Yeah.
the other process is attempting to enter the
Yeah.
critical section?
Yes. So it's coming up with a case like that. Yeah.
Say that again? No. You have to explain that for the rest of the class, okay?
So
Let it not be a conversation just between the two. Okay, so please explain.
So
So what did Diganta say?
so that process one only tries to enter the critical section, so whenever process 2 is already in the critical section, so it's being scheduled like that. So process 1 never actually gets the chance to enter the critical section, because whenever it tries to do so, process 2 already is in the critical section and it can't proceed.
It can race ahead.
Yeah.
Race ahead, huh?
Yeah.
So even if it is given a chance, okay, it would.
So I think we can do a CTL property. So
No. Let's not get into the CTL property, okay? Because they have not seen CTL yet, okay, in full-fledged thing. No, you can try, okay? The best thing is, go ahead.
yeah, okay.
But I think it will be difficult for them to understand this thing. What I suggest is, let me cover what CTL. This is what I'm defining today, and I'll go through some examples and so on, so they will be acquainted, okay? With
And the other mutual exclusion algorithm, I think I put it in the homework assignment also. So
which
to
one?
model it to the one that ensures starvation freedom.
Yeah, but that I had shown in the class.
Yeah, but as part of the new encoding it in USM.
You code it in USME and then check it. Okay,
Yeah.
so let's so we'll decide on that. Okay.
Okay.
Does everyone understand why this particular thing, as stated here, was not satisfying, like what Zubin explained? Hello?
Yeah.
Okay. So so anyway, this you need to upload these things as well, Zubin, because you have not.
They're in the GitLab
They
repository.
are now, okay. So you guys, you have to try. The next assignment will be going very soon, and there'll be simple ones, okay? But for you to get acquainted with, running USMV and then trying a few things out on very simple examples. So so please do run, and before that, you can even use these examples to rerun and make modifications, and then do things, do some experiments on your own as well. And if you have doubts, please come back. Yeah. Okay, this was actually good. I think this was instructive. Yes.
Okay, so I'm.
Thank you. Yeah.
can carry on.
Okay, now I'm not in this order, so let me go back, go to something. Okay, so CTL. So formally, informally, CTL is a sublogic of CTL star. Remember that CTL star had state formulas and path formulas. Okay, CTL is a sublogic of CTL star, where the path quantifiers and temporal operators always occur in pair, in the sense that as soon as you do a temporal operator, then you will have to immediately follow that with a path quantifier. Okay, convert that into into a state formula. So formally, this is how a CTL logic is defined, and my informal statement will be clear as soon as you see this. So if P is a predicate, an atomic predicate, that is part of CTL. If F is a CTL formula, then all these things, okay, are CTL formulas. So remember, taking a negation is a CTL formula, and AX, AF, AG, EX, EG, EF, when applied to another state formula, is a CTL formula as well. This is what I mean, okay? In CTL star,
So
you
could you clarify what is path quantifier and what is temporal operator here?
okay. X, F, G are temporal operators. You remember that? So they are what temporal operators are used to construct path formulas. Yeah. So that I have already defined in CTL star. So X, F, and G are temporal operators. Okay, so they take another path, a path formula, and then extend that to another path formula, and they are, and we define the formal semantics of that over paths. So what the restriction here is, whereas in CTL star, you could apply multiple path temporal operators, that is path formula constructing operators like X, F, and G, before you encapsulated that with A or E, the path quantifiers. Here, A and E are the path quantifiers. What CTL restriction requires is that you will have to apply an A immediately after applying the temporal operator. Okay, so that's what the restriction is. And similarly for binary operators. Okay, so you can do and or, but it requires, remember that until is also a linear temporal operator that constructs path formulas. And here also it requires that you have to apply a quantifier, A or E, before, in the process converting that into a CTL the state formula, before you do that. So in other words, CTL can be considered as a subset of CTL star formulas generated by these special CTL operators. So AX, AF, because they have to, it restricts you to apply them in jointly in pairs. So you can consider these as special operators of CTL. They have the same semantics as in CTL star. Okay. For example, so question, okay, so I'll give you some examples of CTL, well-formed CTL formulas, and those that are not CTL formulas. So is this a CTL formula? It is not, okay, because See, I'm now, it requires that A should X should be, you can't be doing any operations on the path formulas. Here, XP is a path formula, GQ is a path formula, but it doesn't, CTL doesn't allow you to do certain muck around with that. It doesn't allow you to apply operators before you, any other kind of operators, let alone even logical operators like this, okay? So that's what I mean, that you will have to do it immediately. See, G has to be immediately preceded by an A or an E, okay? So this is not allowed in CTL. It is a well-formed CTL star formula, but it is not a CTL formula. This is the restriction of, as per this definition, is this a CTL formula?
Yes.
Yeah, because yes, that is correct. Okay, so AF and EX, they appear together. This AND is okay because it is a conjunction of two state formulas. Okay, and therefore that kind of logical operation on state formulas before you apply another CTL operator is okay, is allowed. It's only what is not allowed is doing things with the temporal operators, constructors of path formulas. That is not allowed. How about this?
Yes.
Correct. Okay. But don't get just misled by the E appearing somewhat, yeah, this E is assumed to be associated with this U, the until operator. Okay. Although it is kind of, removed because this is a binary operator, this E is associated with U, and therefore it satisfies this constraint that this temporal operator has to be immediately preceded by quantified thing. How about this?
No.
Yes? No answer?
No, it won't be.
What? Hello? Someone tried to say something. So let me ask you a question. Is this a state formula or a path formula?
This is a path formula, so it should
The path formula, okay? So, I mean, even by that account, it cannot be a CTL thing. I mean, it's not even a CTL star formula, because a CTL star formula eventually has to have a quantifier, okay, to make it into a state formula at the top level. So you could put an A or an E to it and then make it into a CTL star formula, but it can never be a CTL formula because it's a path formula, even if you put an A on it. Okay. Now you can have AF, EG, EF, AG. They are all CTL thing. Okay. So they are all well-formed CTL formulas. So yeah, another fragment of CTL star, which is actually a fragment of CTL itself, is something called ACTL. It is the sublogic of CTL. Sorry, ignore this NNF here. Form restricted to using, yeah. Well, this is in NNF. Yes, yeah. Okay, but basically it is restricted to using only universal CTL operators. Okay, you couldn't use E or those kind, E, and then so on. Yeah, there is a further restriction here. So, that in this, when I define this ACTL, all the negation has to be at the atomic level. But let's not worry about ACTL right now. Let's concentrate on CTL and another fragment, and we'll visit this later on. In any case, so the ACTL star is similarly the sublogic of CTL star. I haven't introduced you to NNF. I will introduce you to that, to what is a negation normal form, okay, very soon, and then you will understand this. So, but suffice to for you to understand that ACTL star is a sublogic where only universal quantifiers are applied. Okay. The reason that that it requires additionally that negation has to be the atomic thing is because if the negation is somewhere up in the not at the atomic level, then there can be a flipping of quantifiers. Okay, it can have the effect of flipping of quantifiers, which you will know, like not of for all becomes an existential quantifier, and that's why it requires it to be an NNF. But for now, okay, even if you don't understand it, bear with me and don't fuss too much. Why do we define these sublogics? Okay, these sublogics are motivated for several reasons, by the fact that they, as a class of formulas, have certain interesting properties. But more importantly for us in the model, studying model checking, they permit somewhat efficiently tailoring model checking algorithm to suit that sublogic. And sometimes, for example, CTL, among all these sublogics, we will introduce one called LTL in the next slide, okay, is even complexity-wise, the most efficient of all other sublogics of CTL star. So the study of these logics, sublogics, people have done it partly motivated by because model checking can be made to, can be specialized to them to make it more efficient. And also because they have interesting properties and their expressiveness, the kind of properties that it can specify also vary and differ. Therefore, studying expressiveness of what these classes of formulas are interesting in their own right. Okay, but for us, as those interested in understanding model checking algorithms, we are motivated by the fact that it is easier to devise model checking algorithm for CTL and LTL, which is another something, as opposed to general and larger CTL star. So now another popular sublogic of CTL star called linear temporal logic, and Zubin showed both of them. Okay, at least he tried to show CTL as well, and I preempted him. Okay, and we will revisit the new SMV things with CTL, once you have gone through this. So informally, LTL is a sublogic of CTL star obtained by restricting CTL star to only that's a subset of its path formulas. So in which none of the two path quantifiers are permitted. So formally, if P belongs to AP, then P is a path formula. Okay, because we have to start somewhere, as we've seen. Path formula, strictly speaking, it's a state formula, but we make exception at that level and included it as a path formula. So that obviously belongs to LTL. If a formula is already in LTL, then you can do any one of these things. You can take the negation or apply any one of the unary temporal operators to construct new path formulas, X, F, and G. Okay? Or if F and G are two path formulas, if they're already LTL, then you can apply any of the Boolean operators. You can take and an or you can apply the binary temporal operator U and R that we have defined. Yeah. So of course, so this is just the path formula subset of CTL star. The question is, we only define model checking at the top level. CTL star is a state formula, and we assume that there is an A or an E. So what does it mean to model check LTL, which are basically path formulas? So for any formula belonging to LTL, we say that phi is satisfied by a Kripke model if an A applied at the outermost level to that LTL formula is satisfied. So in other words, so LTL formula is implicitly assumed to have one quantifier, okay, at the outermost level. And so what this then means is that the F is just a path formula. So what it means is that it is satisfied by M if every path from every initial state satisfies the every path satisfies the LTL formula. That's how it is interpreted. Is this clear? Okay, we'll see some examples. So, if you have any questions, please stop me, okay? That is right. That is, phi holds in M, an LTL formula phi holds in M, if it holds for every path pi from every initial state of M, okay? So that's why that is the same as putting an A and then interpreting this as CL formula. But we normally, when we do LTL model checking, we talk about LTL, we ignore this A and we will assume that is implicitly there, okay? And that the meaning is, the implicit meaning is that this is what, when we say what we mean by phi holding for M, okay? Then it holds for every path originating from every initial state of M. Here is an interesting aside that you can do. So although, as I just now said, implicitly there is an A, you can kind of also check if for an LTL, if there is an exist, okay? I mean, with an exist quantifier, by actually checking if M, the A of not a phi does not, is not satisfied by M, okay? If, yeah, by actually checking A applied to not a phi, that is, you take the negation of the LTL formula, check if it is satisfied by M, which implicitly means putting an A and then doing it. If that is not satisfied, then what does that mean? There must be a path from some initial state for which not phi holds, okay? I mean, not phi does not hold. Therefore, there must exist a path for which phi holds. So, in other words, LTL model checking is really like putting a path quantifier at the topmost end. The rest is all just a path formula. Okay. And why it is interesting? Why do all these things? I mean, why is it interesting to do LTL? Because if you, like I said, okay, when I introduced model checking, we said we could view the behavior of a Kripke model as a set of paths originating from any one of the initial states, or we can have branching logic, okay, which considers the tree structure, okay? So LTL is one which is interested in proving properties about all paths originating from the initial states. And CTL is, and CTL star in general, is a logic that also is able to express and prove properties about the branching behavior of systems. Okay. Okay, so now some examples to kind of wake you up, if I may say so. So here is a transition system. By the way, this example I've chosen from a book, one of whose authors is Catoan. I'll also upload this book. This book is very verbose, okay, but it can, in some chapters, complement what I have designated as the reference book for the course, because there is one good feature about this book. It has tons of examples, okay, and it is more geared towards automata-based model checking than symbolic model checking. But still, he discusses all these logic and so on. So every now and then, I will also put some selected chapters of this book that you may want to visit and look at. And especially if you want to work out examples, this book has tons and tons of examples. They're very good. Okay. Okay. So first I will illustrate LTL, okay, that we have defined. And then I will ask you about, then we will look at CTL. So I've deliberately not marked any state as an initial state here, okay? It's because the questions, this is a simple game that I want to play with you. So first I'm going to give a list of LTL formulas, okay? Look. Here, they're all path formulas, okay? You don't see any quantifiers, path quantifiers, either A or E here, okay? They're LTL formulas. When I say, yeah. So, and what I ask you is, so these, I can ask this question, are they states here, which are the states, 1, 2, 3, 4, in this transition system shown here, for which this path formula is satisfied by every path originating from that state, or which are the states for which there exists a path that satisfies this path formula. You see, LTL model checking normally is only for all. Just for playing this game, I also want you to give answers, even if there are some states there for which there exists, if not all paths, some one or more path for which this path formula could be true. So this gives you both an understanding of what an LTL formula is, and also gives you, it triggers your memory about checking path satisfaction, okay? So let me take one at a time. X, X, Y. Is there a state which among 1, 2, 3, 4, for which every path, infinite path, originating from that state satisfies this formula?
State 1.
You have to speak up. I didn't hear.
Am I audible? Hello?
Yes?
Hello. Yeah, state 1.
Is that the only one? Why does it, yeah, so what does this mean, X, X, Y?
As well.
What does it mean, X, X, Y? It is true.
Next to next state will be Y.
Yeah, it is true of a path if it is Y is true in the next to next state. That is if I index it from 0, it has to be true in index 2, correct? Yeah? Yes. So Y next to next. So I'm sorry, next to next, okay? It is x, x, y. Yeah. So if it is, yes, it is true next to next. Okay, it's not in one. It holds in two. Correct? Yeah. And actually, that's the only state for which this is true in. I mean, that's the only state for which it is true. Actually, this is not. Why is it true? Okay, that's the only state for which on every path it is true, because you go from here to 3 and 2. It is okay. So what are the paths from 1? Okay, there can be path that circulates between 1, 3, and 2. Okay, or you can have 1, 3, and 2, and or ends up circulating in 2, 4, or it can alternate between those two things. And all those things, because it passes, every path passes through 2, therefore, in the next to next state, y holds good. Correct? So he was right that this, for all, it is 1. How about exists? What are the states in which there is, it may not hold good for every path originating from that state, but they may exist.
Two itself.
Correct. In addition to 1 of course is a candidate because it is true. And in addition to that 2, yes, correct. So this is 1, 1, 2, okay. Let me now move to not XSR, but the third one, FY. I don't have the answers on the slide, okay, but
I think all the states would eventually lead to it.
correct, okay. 2 is certainly a state that is on every path, okay. You know, so on every path, So 2 is true. So you're right. F of y holds good for all states, and therefore, obviously, it is true for all here and here as well. Now let's do g of f of y. What does g of f of y mean?
So essentially, it means y happens infinitely often, right?
Yeah, so yeah, you're right. Y happens infinitely often. But to be, to be more detailed than that, see what it's saying is, it is true of those paths where f of y happens continuously, okay? So that's how. So g of f of y means this f of y, the subformula f of y should be true forever. That is, at every point on that path. And if I want to misuse it, at every point on that path and every state, which means that, it should be true at any point. There must be a point after which, at every point on a path, there must be a point after that where y holds good. Okay, so that's why it has the effect of saying it holds good infinitely often. So no matter how far down the path that you go, from that path there is another point later than that at which y holds good. So that's exact. So that's why this particular pattern is ensures that y happens infinitely often. Okay, so which paths is it true, or which state from which every path for which it is true?
All the states.
Correct, all the states. You're right. So it is true for all the states, and obviously E is true for all of them as well. So let's do the same thing for GF of G. Okay, this is once again claiming that G has to happen infinitely often. Okay. Yeah, I'm gonna go an extra 5 or 10 minutes today. We started 5 minutes late, and I want to finish up at a logical point. I hope you don't mind. So, yeah,
State
we're at
one holds, right?
G of f of G. Yeah, you were saying something?
Yeah, if there is a path with state one, then it will always hold that G is occurring.
Yeah. What?
I mean, say take the path 1, 2, 3, and if you repeat that path infinitely often, then G will be occurring infinitely.
Correct.
But there can be paths from one where G doesn't happen infinitely often.
Yeah, so for that, state one has to occur, right? So
So what are
it's
the paths once again? So there is a path, yeah, an infinite path which goes through 3, 2, and 1, on which G happens infinitely often, but that is not true for all paths, correct? Because yes, so if there is also a path from 1, for example, which goes through 3, 2, and then it can just circulate from 2, 4, 2, 4, 2, 4, okay, for which it does not hold good. Okay, so from 2 also that is the case. From 2 there is a path where it does not hold good. There is a path where G never holds good. Similarly, from 3 there is a path from on which it never holds good. From 3, of course, if there is an infinite path that circulates through 1, 2, and 3 for which it holds good. So there is no path, okay, for no state from which every path for which every path satisfies this G f of G. Okay, so but there are some states for which it is true. Okay, there are some states for which there are some states for which there exists some path for which G happens infinitely often, like it is here. Yeah, and so on. Okay, so that is the idea. Okay, so I want to. So how about let's take the until operator. These are a kind of a weird until thing. So not B until B. What does not B until B mean?
so throughout the path there will be only one occurrence of B.
Throughout the path? Say that again.
Yeah, so throughout the path there will be just one occurrence of B.
That's actually not true. So first of all, recall the semantics of the until operator. It has it imposes two constraints. It says that B should eventually hold good. Okay? It has the constraint that B must eventually hold good up to the point, not up to the point prior to from start to the point where B holds good, not to the point before it. Not B should hold good. Okay, I mean if B holds obviously, so if B but doesn't hold, not B will obviously true. So so basically it's saying eventually B has to be true. Okay, that's all this thing is saying. This is another way of saying B eventually has to be true. But what you said, the person who's just said, it says that B has to be true exactly once or something like that. You said that is not true. Once B becomes true, eventually becomes true, it doesn't matter what what B is after that point. It can, so this until operator doesn't impose any constraint after the point when B becomes true. B could, for all I care, can be continuously true after that, or never true, or alternate, whatever. Okay, so that's
So
what
this is like f of b, right?
well, this is like f of b, exactly right. Okay, but you will see that sometimes putting these not b's, in combination with other things will get you certain things. Okay, where you could sequence precedence of events, etc. If especially precedence of events, that something should follow something and something should follow something before something. All those kinds of properties are will eventually need you. Okay, the until operator. So you're right, okay, for the purpose of this thing. So this is like B, okay. What states, yeah, so this is like eventually B. So what states for which every path satisfies that?
Four.
Yeah, 4. I mean, 4 satisfies that because it is immediately B is true, and therefore every path that is originating from that satisfies that. Even 2 does not, none of the other ones satisfy because they can circulate in infinite paths where B is never true. Okay, and so on. Okay, so you can work. So since I have 5 more minutes, so you can do this exercise. Now the next thing that I'm asking is, can you make CTL formulas that are equivalent to these things? That's the next exercise, okay? You can fill in the for all and exists at your convenience, okay? So what I'm asking you is, now the exercise is to construct CTL formula that are equivalent to that, okay? Which means, so obviously, yes, okay? When I say equivalent, what does it mean? So as I said, equivalence means they should be true. Both of those formulas should be true on all models, okay? So when, as I said, an LTL formula implicitly has an A at the topmost level, whereas CTL, as we have defined, has AX, EX, etc., etc., okay? So first take the easy cases. So if you have f of y, which is like AF of y, that itself is a CTL formula, correct? Therefore, for all these things which only have one level of temporal operator, path constructing temporal operator, it is easy to see that, okay? Because they're already, the equivalent formula is AF of A, putting in A, okay? And this is already in CTL. Do you agree? Yes? Yeah. So the fun begins only when you have these kinds of nested formulas that have nested temporal path constructing operators like XXY, GF, and things like that. Okay. And these will be equivalent to that because obviously AF of I. So they will exactly correspond to whatever the results of for all here. Okay, they'll exactly be those states for which you would have filled up this for all thing. Now, how do you construct a formula for X of X of Y in CTL? Obviously, if you put an A at the topmost level, that's not a CTL formula, correct? Because that violates this restriction that every temporal operator has to be immediately preceded by a path quantifier, okay? Therefore, doing AXXY doesn't hold. So the question is, one obvious thing is, you put quantifier. So you could do this, AX, AXY, AX, AXR. I'm not saying they're equivalent, so I'm asking the question. That's certainly a CTL formula. So is that my question I'm asking is that always an equivalent CTL formula? I mean, maybe not always. In this case, are they equivalent? Is X xy, that is axxy is equal to axy. This is something for you to think about, okay? So what does this axy say? It says that this is true of a state, okay? All CTL formulas are true of a state, okay? Now here also this is true eventually of a state, but for all paths. So this is true of a state for all those states for which every path from that state, the next state in that, every next state from that, AX means every next state from that state, every successor of that state should be such that every path, I mean, every successor of that state should have Y holding good in that thing, okay? So if you're in doubt, this is equivalent to this, okay? So if you're in doubt, you can write out the branching thing, okay? It's true of a state if it is true, if AXY is true in every successive states, okay? It's successive, okay? And AX of Y is true for the successor state if it is true for every successor of that, and which is what this thing is, and therefore this is exactly equivalent to this, okay? And in this, yeah, so is for XXR. Now, the question is it true for this one, for GF, Y and GFG, okay? Now, we are running out of time, but you will see that it is true even for this, okay? And one way to ensure this is draw the branching computation tree and then reason about. And the important thing to notice is, whereas GF of Y, it only imposes constraints on path, okay? Once you get the paths, you enumerate the paths and then you apply the criteria, whereas here it is about the state, okay? So you'll be asking the question, if every path originating from a certain state is such that every state, AG says, if every state on that satisfies AF of Y, okay? So, usually when you will notice that when it begins with a G, putting in a universal quantifier will make it equivalent, AG of AF of Phi, okay? So, but the real question is, can you do this all the time, okay? So if you have, suppose a phi is a CTL formula, and you derive f prime by dropping all the quantifiers in CTL, from that, okay, from phi. So my question is, then you get a LTL formula, correct? So if that is that LTL formula, that is what I'm saying is this is an A of some, it's a CTL formula starting with A. So if I drop all the quantifiers from this, except that the leading one, you will of course get an LTL formula. So the question that I'm asking is, if by dropping all that, the two are equivalent, okay? The answer is no, not all the time, okay? And we will see why that is, that is so, okay? So there are certain situations, and well, why that is so, you should have guessed, because there is a state-related constraint that imposes on the path, whereas here that is not the case, okay? It just views those as individual paths, okay? And whereas here, when it looks at these paths, since it's the branching behavior, it then asks that the states on that path need to meet the state constraints as specified by the sub-formula, and that usually does not. Specifically, if you had f of g, okay, g of f is always equivalent. If you had f of g, you will see that that is not true, okay? And And it turns out, okay, you know, I'm not rushing here, but I just want to make a point so that, you know, we will revisit. So don't worry. So there is another interesting question, okay? Whenever, if there is a very important result due to Clark and a few other people, that when you drop from a CTL formula all the quantifiers, okay, to get an LTL formula, if those two things are not equivalent, then it turns out that if they are not equivalent, then that CTL formula has no representation in the LTL class. You get it? So in this case, they all happen to be equivalent. As I told you, we will see next time that when you have f of g, that's a special kind of very important property. When you have f of g something, it says that eventually you will get to a point where g persistently holds, that g holds forever. That is called a persistence property, that it says that eventually you on a path, you get to a point where g holds continuously, okay? That one is not equivalent. I mean, AF of G is not equivalent to, I'm sorry, AG of G is not equivalent to F of G. So it turns out that when that is not equivalent, this CTL formula is never representable in LTL, okay? You know, to get some intuition, you know, we will see that particular example. And f of g's happens to be the persistence property, also happens to be one example where f of g is also not representable in a CTL. Okay, there are reasons you know, for that. So that is a very interesting kind of property, and therefore that leads us to this in hierarchy of that describes the relative expressive part of the sublogics of CTL star. So you have CTL star here, which is obviously more expressive than any of its sublogics because it includes both LTL and CTL. But it turns out that LTL and CTL, they are sublogic of CTL star, but individually they are not comparable with each other in the sense that there are some properties that are expressible in CTL but not in LTL and vice versa. Okay? And we will see an f of g, the persistence property, is one such property that is expressible in LTL but not in CTL. And f of ag, which is different than f of g, is expressible in CTL but not in LTL. And that's why you have this kind of a picture here. Of course, ACTL falls completely within CTL, and ACTL star, you know, falls within CTL star, you know, but it is, yeah, ATL star is something which is incomparable with ACTL and CTL. So this is what the thing is. So in the next class, we will see a few more examples, and we will, you know, get more insight into why CTL, you know, certain formulas are not representable in one, are representable in one, but not in the other, and some insight into that. Okay, and then we get into fairness, the fact that certain formulas are not representable in CTL but only in LTL has consequences for expressing the fairness constraint itself. Okay, and therefore, you know, so there, that raises the question: how do you even check fair, do fair model checking? And that's why these things are somewhat important, you know, to understand. Okay. Yeah, so I will stop here. Sorry for going late. So I do not wish to ask you questions unless you know, there are some pressing questions, because we are already well past the deadline. Yeah, I mean the thing. Okay, so I'll see you on Wednesday. We will sort out, okay, the new SMB fairness specification thing, and that Zubin will. He already clarified why that was the case, but it was still a little bit, we were unsure as to how exactly you specify the fairness constraints in USMV. There was some confusion about that. That also we will sort out. Yeah. Okay. Thank you. Bye bye. See you on Wednesday. Thursday. I'm sorry.